As we examine the world around us, we find it to be composed almost entirely of compounds in which different kinds of atoms are bound together. But why do atoms form bonds? Consider a hot cup of coffee. It naturally cools down over time, releasing its energy and moving to a lower energy state. Similarly, a marble at the top of a hill will naturally roll down, seeking a lower potential energy state. Systems in nature tend to favor states of the lowest energy. This principle also governs how atoms behave. Let's look at the simplest atom, hydrogen, consisting of one proton and one electron. It's usually found on Earth as hydrogen gas, H2, rather than individual atoms. But why is that? To understand it, let's look at the energy change during the formation of an H2 molecule. The formation of hydrogen gas from individual hydrogen atoms releases energy of 435.8 kilojoule per mole, which is released as heat or light, making the H2 molecule more stable. Then isolated hydrogen atoms due to its lower overall energy. Now we know why atoms bond together, but what makes them come together? And once they're together, what makes them stick? Now imagine the electron not as a tiny particle orbiting the nucleus like a planet around the sun, but as a fuzzy cloud of probability surrounding the nucleus. This cloud's shape and size are described by Schrödinger's equation, which helps us understand where the electron is most likely to be found. Not much happens if the atoms are very far apart, but when hydrogen atoms are brought close together, there are two unfavorable potential energy terms: proton-proton repulsion and electron-electron repulsion, and one favorable term, proton-electron attraction. The positive charge of the proton in hydrogen atom 2 attracts the electron of hydrogen atom 1. Similarly, the electron of atom 2 is attracted to the proton of atom 1. We can plot the total energy of the system as a function of the distance between the hydrogen nuclei as shown in this graph. The 0 point of energy is defined with the atoms at infinite separation. At very short distances, the energy rises steeply because of the importance of the repulsive forces when the atoms are very close together. The bond length is the distance at which the system has minimum energy. As we move from right to left, you can see what happens to the energy when the two atoms go from being far apart to being closer together. The dip in the graph represents the lowest energy state of the two-atom system. If the distance between the protons gets any smaller than that, the energy goes up significantly. And if the distance gets larger, it also goes up, although not as steeply. So the two atoms find a natural sweet spot such that they are both happier being in a lower energy state together than when they were farther apart by themselves. It turns out the energy of this two-atom system is less than the energy of two separate one-atom systems. This is the reason if a bunch of hydrogen atoms are near each other, they will naturally combine to form a molecule of H2 rather than float around by themselves. Now, after understanding the formation of the H2 molecule, you can explain why other atoms also form molecules to adopt a lower energy.